All right, guys, so we're going to continue our discussion here with genetic algorithms. And genetic algorithm is a type of stochastic beam search, right? We just finished talking about stochastic beam searches, and they're basically, remember what they are, they're hill climbing algorithms where you have, instead of one current node, right, you start off with and pursue k nodes, right? So, 10, 20, 30, 40, whatever. And then the hill climbing algorithm runs on each one of those nodes in parallel. And so genetic algorithms are a form of that. They do something slightly different. They have sex. No, I know I got your attention now, don't I? They have sex. So the successor states are created not through an actions function, okay, like what we had, in a result function like we had in earlier algorithms. Okay, but they're going to use this thing. Well, you'll see. We're going to have a function that does what's called a crossover, and so what happens is that those successors, they get created as a result of a joining of two parent states. So yeah, this is what this means. It's going to be used sexual reproduction. The successor states are done created sexually rather than asexually, right? So the hill climbing algorithms that we looked at so far, you had your current node, you generate all the possible successors, and then you pick the one that has the best score according to its objective function, right? So then that state, that node, that node with the state that had the best objective score, well, that becomes the new current, right? So that kind of takes over. That's the next generation, if you will. But here, instead of just having one node give way to one node, you're going to have new nodes become generated by two parent nodes. So two of those nodes, or two of those states, maybe I should say that instead, because we're not necessarily going to need nodes here. Two of those states are going to combine and exchange information. And that exchanging of information is going to be doing some crossover, just like from evolution. When two individuals in a population meet and do the nasty, and they exchange genetic information to make their kid, right, or combine their genetic information. That's what's going to happen here, is that the new individual that's going to move into the next generation is going to be a combination of two parent states, okay? And I'll draw you a picture of this too. So here's the idea. Here's a couple more points, then I'll draw a picture here. Draw a picture of a genetic algorithm. Don't get any funny ideas. So you start with those K states, right? Those K initial states, like in the beam search, right? And they're randomly generated, and that gives you your population, your initial population. And so you're going to go through generations where where a population gets replaced by the new successor states to make up a new population. So you got the population of the parents who get together, do the ditty, and then create a new population of children, and then you continue the search with the new population of the children, who then become the parent, and et cetera, et cetera, et cetera, right? Lather, rinse, repeat. So the parents are gone. Who cares about them anymore? They died off. They're not even considered in the picture anymore. Kind of like with the hill climbing algorithm. Once you moved on to the successor, right? Who cared about the parent node? Okay, so each state is an individual. And you have to come up with some kind of way to encode the states, right? So however you want to do that, there's going to be some kind of a state that's going to be representing that individual. And typically, usually, it's over some alphabet, some finite alphabet, right? And that alphabet could be whatever, okay? Whatever works for the problem that you're solving. Often, it's a string of bits, right? Where different positions within the bit string represent different pieces of genetic information, as it were. If there's a possibility of three different pieces of information, you want to represent, 1, 2, or 3, well then 2 bits of the bit string for that position could represent 3 different pieces of information, right? Or a piece of information that could be trinary, okay? Or if it's just binary information, well then in 1 bit, okay? Yeah, so I mean, the reproduction, now this is where it gets kind of cruel. There's a function that you use called the fitness function, okay? And so the fitness function, what it does is it evaluates each individual within the population. So, you're checking out each individual going, oh yeah, I want to reproduce with that individual. And so you write a function that's basically like your objective function or your cost function, right? Or heuristic function, where you're given some kind of estimate of the overall value of that individual from the population. Remember, the individual is representing a state. That state is represented using some kind of finite alphabet, or often it is a bit string that's being used. Why bit strings? Faster. Bitwise operations are faster. You could use other representations. You could use arrays of characters if you want to. I mean, you could use arrays of integers. You could use, whatever. But bit strings are going to give you your fastest performance, right? Because bitwise operations are just incredibly fast. So yeah, that fitness function, you feed into it an individual, and then it evaluates that individual, and then it returns a score, right? And so the better the individual by some metric, right, by some objective measure, the higher that score is going to be, and then the probability that a particular individual is going to be chosen to become the parents, or to be one of the parents of a child, right, to be able to reproduce, it's going to be based off of this fitness function, and there'll be some probability that's built into it. And there's an example here for the 8 queens problem, which I'll walk you through. I'll grab my whiteboard here in a second. But the way they did it in that example is they said, all right, well, let's make a ratio of all of the individuals in the population, and that ratio is going to be based off of their fitness score, right? So if you got 100 individuals in the population, and the total of all of the fitness values of everybody in the population, say 200, right? And one particular individual is worth 5, well then their chance of getting picked to reproduce is going to be 5 out of 200, okay? It sounds a little bit more complicated maybe than it is, but yeah, so 8 queens, we'll talk about that. I'm going to switch over to my whiteboard. I think I'll do that right now, so I'll pause and be right back. All right, so let's talk about that 8 queens problem that the textbook uses as an illustration. And let me walk you through it, maybe give you a little bit better understanding. Remember, with 8 queens, we're talking about trying to arrange queens, 8 queens on the chessboard in such a way as none of the queens are attacking each other, right? So I won't draw an entire chessboard here in the interest of time, but you'd have, your 0th row, your 1th row, your 2th row, your 3rd row, and so on. And then you'd have your 0th column, your 1th column, your 2th column, your 3rd column, and so on. And so you might have one particular state might have a queen there. Another state might have a queen there. Another state might have a queen there, right? And then, maybe this particular column has a queen, maybe here, okay? So that is one particular arrangement of the queens, which is one state. Now, how could you represent that? I've been saying multiple times, represent it however you want, doesn't matter. In the text, as long as it works, in the text they talk about, a couple of options here. One might be an array of integers, right? So you'd have an 8-element array, okay? 8-element array. Is that 8? 1, 2, 3, 4, 5, 6, 7, 8, yeah. Where the first element corresponds to column 0, the second element column 1, 2, 3, 4, 5, 6, 7. And then in each one of those elements, you would just put the row number where the queen's at. So for this first column, the queen's in the 0th row. For the second column here, the queen's in the 3rd row, right? And then for the 2th column, the queen's in the 1th. And then for the 3rd column, it's in the 2th, right? And so on, okay? So that would be one way of doing it. Another way of doing it would be using bit strings, which would be more efficient for a couple of reasons. One, it'll take less memory. Another is that bitwise operations are faster than array processing operations. The text talks about having to have a 24-bit long bit string. Well, why 24? Well, think about all the possible positions of where the queen could be, right? It could be anywhere from row 0 through row 7, right? That's 8 possible rows. And so how many bits do you need to represent 0 through 7? Well, 0, 0, 0 is 0. You need 3 bits. 0, 0, 1 is 1. 0, 1, 0 is 2, 0, 1, 1 is 3, and so on. Okay, so you need that to represent where the queen could be in each possible row, right? But that would cover one column, right? What about the next column? Well, then you need another 3 bits. What about the column after that? We need another 3 bits. So 3 bits required to give you a number from 0 through 7 times 8 columns equals 24 bits, right? So the equivalent bit string for the configuration of queens that we see here in my little example would be, it'd look kind of like this. Well, we'd have 0, 0, 0 for that queen there. Now for the queen in the second row, right, the next 3 bits would be used for that. So we would have, that's in row 3, right? So 0, 1, 1, okay, and then for the third column here, that's 0, 0, 1, and then for the fourth column, that's 0, 1, 0, etc. Okay, so that's 24 bits that you need to represent all the possible states. Okay, now what could you use to store those bits? We need these 24 bits. So you need at least 6 bytes, don't you? 6. Well, no, 3 bytes. Can't do math apparently. You need at least 3 bytes. Well, a short's not going to do it. If you're thinking C++, you need to have like an int, right? Now that's 32 possible bits. You're only using 24. The lead 8 bits wouldn't be used. Who gives a crap? They'd always be zeros all the time. Fine. Then you just use bitwise operations like bitwise shifts or whatever to pull the bits off, and then be able to evaluate them if you needed, or you could use bitwise ands or bitwise ors. I can never draw these stupid ands, bitwise ands or bitwise ors, to change the bits, compare them, etc. Okay, that's a lot easier than doing array processing, isn't it? All right, so that's how we could represent a particular state. Okay, now we need to have a fitness function, right? We've got the representation, okay, and then we need to be able to evaluate. We need an objective function, which in genetic algorithm terms they call it a fitness function. I can't spell either apparently. Okay, and so all you're doing is feeding the state in, passing that 1 byte or passing that array of integers into this fitness function, right? And it's going to evaluate the state, and it's going to spit out some number, right? So the textbook talks about counting how many queens are not attacking each other, and then using that as the metric. And so the best would be what in that case? If you got 8 queens that are not attacking each other, I suppose. But I mean, you could come up with it in a few different ways. This queen right here in 3 different directions is not attacking anybody. This queen, and you just have to work out the details for counting all that up. So one particular state might be evaluated at, I'm just going to make these numbers up because I'm not going to do the math on it in the interest of time. And you can look in the textbook for their examples. But let's say that this particular state evaluates to 8, right? Then there could be another state where the queens are arranged differently, 3, 1, 2, 4, 4 or something, right? And you feed that in the fitness function. And then the fitness function for that separate state spits out 12, right? Well, you would take a ratio of, add up the 2 here. 8 plus 12 is what? 20, right? So that's a total of all of the fitness values for all of the individuals in this population. Now in this population we only got the 2 individuals just to keep it simple. But you could then take that first individual is worth 8, divide that by 20, and that gives you a percent, right? So divide both by those by 4, that's 2/5, right? So 2/5 is what, times 20 here, that's 40%. Is that right? No, I don't think that's right. No, that's right, 40%, right? So 40%. So there'd be a 40% chance that the state that has an evaluation or has a fitness value of 8 would be chosen to reproduce, right? And then the guy that's 12/20, right? Divide both of those by 4. Well, that's 3/5. Okay, so there'd be a 60% chance that the state with a fitness value of 12 would be chosen. Okay, so that's the idea there. So how could you store your population? Now remember, with the genetic algorithm, you start off with a randomly generated population, right? So you come up with some kind of random state generator, right? Maybe create a function for that, and then you could create an array, and if you're doing it with bit strings, an array of integers, okay, or a two-dimensional array if you're gonna be crude about it and do an array of integers representation, whatever. You just have to pick which one that you're gonna do. And so then each element of this population array would be one of the individuals, okay? And so then what you do is you run through your population once you've generated it, right? Because you've got this create individual function, whatever you want to call it, create individual. Okay, that generates a random state, which you then copy into each individual element, right? That creates your initial population. And then once you've done that, you have some kind of loop where you feed the population into it, and then you run the fitness function on each individual in that population. And then each individual in that population is going to be worth some value, 5, 8, 3, 2, whatever. Okay, sum all of those up, just like I did with the smaller population with the two individual populations size, and you get a total overall fitness for the whole population. And so then the population fitness total, I guess. Okay, and then you could just divide, take that 5, divide it by that total, and that would give you percent. Maybe that's 27%, not 0.27, but 20%. Maybe the 8 is 33%. Maybe the 3 is like 4%. Maybe the 2 is like 3%. Maybe the 6 is like 10%, whatever. Okay? And then once you've done that, or part of doing that would then be, as you're going through, saying, all right, well, you've got a 27% chance of being picked. I'm going to roll a die. I'm going to roll a 100-sided die, a D100. Those of you who are nerdy enough, you know what I'm talking about. A D100 to see if this guy gets picked, right? And if he gets picked, congratulations, you get to reproduce. Okay. Then you move on to the next individual, and you roll the dice, and maybe they don't make the roll. So you skip over that 33% individual, right? If you had to roll 33 or under, and the random number generator rolled 50. Oh, sorry, you don't get to reproduce. Move to the next individual. Oh, that guy rolled 2. Whoa, this ugly guy is lucky, right? He lucked out. He got a Porsche or something, and so he's going to get picked to reproduce. Okay, and then you come down here. The 10% guy rolls to reproduce. Okay, and then you keep going. You find another individual down here who's going to reproduce, right? And so on, right? Some of these people are going to get skipped over. Some of them are going to get picked. Some of them could get picked twice. Okay, that is a thing. I mean, if you look at the algorithm, you'll see that it goes through, and there's X and Y, right? And X and Y are neighbors. Okay, and so you might get a second chance to get picked. Okay, but anyway, once you've picked who's going to reproduce and you pair them up, right? So these first 2 guys who got picked, you can pair them up, right? And then the next 2 guys who got picked, you can pair them up. Okay. Now there's going to be, within that individual, the information that's encoded, right? So, whether it's a bit string or array of integers or whatever, let's say that we've got, I'll just pick some numbers at random here, 8, 6, 7, 5, 3, 0, right? And that's just 6 numbers. You'd have 8 for 8 queens. I'm just going to go with the smaller numbers to speed this up. 7, 1, 2, 3, 8, 4. Okay, and then you've got 6, 6, 6. The chess state of the beast. 7, 7, 7, and then maybe you got 1, 0, 2, 0, 1, 2 or something. Okay, now when you have these two individuals, and these two individuals, what they do is they get fed into a crossover function. Okay, crossover function. Okay, and what happens is in this crossover function is that you randomly pick some crossover point. Okay, if you've got if you got 6 numbers in here, maybe you pick a crossover place that is from between indexes 1 through 4, right? It just depends on how you want to code it. I'm just throwing ideas out there, so you get the big idea. Don't be sitting there taking notes and go, oh my God, I got to memorize everything. He said that it has to be 1 through 4. No. You come up with some scheme to pick a crossover point, okay? And you might have to experiment and fine tune to try to optimize your results, okay? But anyway, so let's say that the random number generator picks the crossover point as being element 2, right? So what that would mean is that you'd be exchanging information, right, between these two individuals based off of that point, that crossover point. And this is where the sex comes in, okay? So they swap, right? So they're going to end up with 2 children, and they swap everything that comes after that crossover point. All right, crap, I didn't draw this good enough. Okay. So these are going to be the 2 children that result. Okay. Right. So you keep the first 2. In this example, I'm explaining. I mean, there's been papers written on this, and if I remember, I'll put a link up to the paper that suggests, talks about, just for your information, if you're interested in reading up on it further, it won't be required or anything, but. What are the best crossover points? How can you write the crossover function? Blah, blah, blah. What are the best approaches to genetic algorithms and all that? But anyway, so the 7530 and the 2384, they switch, right? So this becomes 7530, and then this becomes 2384. So there's the swapping of genetic information from the parents to the children, okay? And then that would happen for all the pairs that have been paired off. Okay, and then there's one more step. Okay, there's one more step, and that step is mutation. Right, this is how we get Magneto and Wolverine and all that. Right, there would be a mutation function where each individual goes into that mutation function. Call it MF. Okay, and then you'd have some percentage chance that a mutation would occur. It's not going to be guaranteed every time, and you tweak it based on experiences or what the problem description is, or just it's like a knob that you can fine tune your search with. Okay, and so maybe you decide, well, there's a 5% chance of mutation on any individual within the population, right? So let's say that the first individual came through the mutation function, and the roll was made and they got a mutation. Okay, so what that means is then you could just pick at random any of these items within the individual, within the state, and then just change it somehow. Maybe there's a 5% chance there'll be a mutation, and then since there's only 6 pieces of information here, you roll a d6, right? Roll a 6-sided die, and it comes up 4. Okay, and so that tells you, well, 3 is going to get mutated. It's going to get changed somehow. And so how do you decide you want to change it? Well, you pick, right? Maybe you roll an 8-sided die and assign the value. Or maybe you just increment it by 1, whatever. However you decide you want to do it. Okay, and so let's say that all I'm going to do is just add 1 to it. Right? Oops, I don't need that last piece because we're not crossing over anymore. So then the final version of that individual is 862484, because this is what they inherited from their parents, but they are a mutant. They got mutated. So that 3 became a 4. That's their final version of them. Whereas there was no mutation in this other individual, so they come out, and changed. Okay, So that occurs for all of the different pairs, okay? And so the result of all of that gives you your new population. The old population, gone, who cares about them, right? These are the new population. This is your new set of K, right? So this is K plus 1. And then this was your original K, right? Call it K sub 0. Maybe I shouldn't call it K plus 1 because that might sound a little too confusing. This becomes the new population. K sub 0 is gone. And then you just repeat. You just do the same thing again, right? Just like with the hill climbing algorithm, you find out who your successor is. You find all of your successors. You pick the best one, and then that becomes the new current. And who cares about the old current? And then you repeat the process. It's just that here you got K individuals instead of just the one. It's a stochastic beam search, right? Remember, beam search had K individuals. This is stochastic because there's randomness in it. That's what stochastic means, or stochasticism. Where's the randomness come from? The percentage chance of selecting the individuals to score, and then the percentage chance of there being a mutation, right? So what's the best percentage chance for mutation? I don't know. You'd pick, you'd experiment. There's also the percentage chance of where the crossover point is too. So there's some randomness there also. What should you make the chance be of that crossover point? I suggested one, but you could pick anything, right? And matter of fact, for the assignment, you're going to implement your own genetic algorithm to solve the traveling salesman problem. And as part of that assignment, I'm going to say, hey, run your simulation, 10 times, and tweak with all these different knobs, right? So, what are some knobs that you can use to tweak the process, the search? How many individuals are in your initial population? That's one. 50,000, maybe 10,000, 20,000. The crossover. Right? Where you decide to do the crossing over, or how you decide to do it, that's another thing. The way you evaluate the fitness function, right? How you evaluate individual units or individuals in the population, because then that affects the percentage chance of certain states being chosen over others, right? Certain individuals. Your mutation percentage, okay? I guess I'll call it MP. That's another knob you can tweak. So you can tweak with all those different settings, and it'll give you different results in your search. Right? You might find, the best state faster, or maybe you'll find better states as opposed to not so good states, depending on how you tweak these knobs. And so, what's the goal of the genetic algorithm here, right? Maybe I should have said at the very, very beginning. Well, think about 8 queens, right? You want to find, in that case, you want to find the best state as determined by, you want no queens attacking each other. So the highest number of queens not attacking each other. Now, in that case, there could be multiple goal states, right? I mean, there could be multiple configurations of those queens arranged so they're not attacking each other. So there isn't just one, say, configuration. There could be multiple ones. But in that case, they're all kind of valued equally. But for the traveling salesman problem, you're hopefully trying to find the shortest distance that you could travel while visiting every single city exactly one time. Now, there could be different ways that you could visit, different orders in which you could visit the cities without having to visit any one city twice, right? But if you put distance into the equation, you might be able to find the best by visiting cities, different cities in certain orders, that will give you the smallest mileage, right? The smallest mileage. Maybe there's a combination of cities that you can drive around California, visiting a certain number of cities in a certain order, so you don't have to visit any of those cities twice, and you don't have to travel any further than you need to. Okay, so depending on these knobs, how you tweak it, you might find a shorter distance or a longer distance. And so for the assignment, I'm going to recommend, hey, run your simulation 10 times, change your mutation function or your mutation percentage, tweak with your population sizes, and then report back what your best overall score is, about your best overall success was. Yeah, and so if you're going to do that, then an easy way to make sure that you can twist all these knobs is at the beginning of your code file, right? Just make some named constants, right? So, const int IP, initial population equals 50,000, right? Or you can even make them variables and pass this information as command line arguments. You can script it. I mean, you can do it in all kinds of different ways. But that's just some things to think about, okay? So let me fly back to slides here. All right, so back to slides here, and this is just summarizing all of the steps I just drew out for you. The idea of a schema is what drives the advantage here, and that's because of the crossover, okay? And basically, what's a schema? Substring where some positions are left unspecified. So, with the crossover function, we randomly picked a point at which data was going to be exchanged. Okay, so right here, what you have is you have a subset of states, right? Any state that begins with 246, okay, and begins with 246. Now there's how many different combinations of states that generate or that begin with 246, based off of these 5 positions. Okay, now matching strings, within that start off with some subsection, those are instances of the schema, and the number of those instances are going to grow over time. Okay, and that's going to lead you to a solution or multiple possible solutions, right? Because what's going to happen is that eventually you're going to home in on a particular solution. You will find that as you go through your homework assignment, don't be surprised if you end up with a population where everybody's the same, right? Because eventually, you're going to have a bunch of individuals in the population that, their substrings all tend to become the same, right? So they all lead off with 246s. Then pretty soon everybody is related to each other in that regard. And then through the random combination of these 5 numbers in the substring, those start dialing in and becoming the same, right? So eventually all of the parallel searches tend to converge onto one particular state. Okay, so don't be surprised if that happens to you, maybe very quickly after a very few or surprisingly few number of generations. Okay. All right, so here's the algorithm summarized for you, the pseudocode for it. You got your population that has to be passed through your initial population, as I was saying in the drawing, that you would have to randomly generate. Right? You'd have k individuals within that population, have some kind of random generation function. The fitness function, which you would have written also to evaluate how fit that particular individual is. The genetic algorithm will return an individual. Let's see here. So you have this outer loop, and then you got the inner loop. Okay, now the outer loop starts off with the new population. So that's going to be who the children are going to be, right? The potential children. Initially, that's going to be empty because nobody's had sex yet. So you got an inner loop, which is going through the population, okay, the existing population, the population that starts off randomly generated by you, and then picks out, 2 individuals from that population as it's traversing through this loop, okay? And you're picking them out randomly based off of, that fitness function, as I gave you in the example. Okay, now as you're picking out pairs of individuals, okay, you identify those pairs, throw them in your reproduce function, and that's where the crossover happens. And then you get a child that is the result, a child or 2 children, right? Depending on how you write this. In the 8 queens problem, you ended up with, in the way I drew it up, you ended up with 2 children each time, right? But the result of a reproduction is going to be a child, and then you check your possibility for mutation, and if it comes up, if the dice come up, for the child to have a mutation, then you mutate that child, and then you add that child to the new population. They become part of the new generation. Once you've gone through and paired off everybody's done doing the nasty, then your new population is done being generated and they supplant the old population. So the original population gone now. They're overwritten by the new population. So it's just like with the hill climbing algorithm, where you start off with an initial node, figure out who all the possible successors are, pick the best one, and then the best one became the new node, and we tossed the old one, and then repeated it. So start off with your initial population, figure out who's going to be members of the new population by this process, and then toss the old population, and then the new population becomes the old population, and then you do it again. Okay. So this reproduce function here is just talking about, doing the crossover. So you got your two individual parents, pick some random number in the string, and then you do that crossover, okay, to create the new individual. Now this says that you keep doing this. See how this outer loop is repeating? Repeat until you figure out, or until you find an individual that is fit enough, or enough time has passed. Now what does that mean? Well, in the case of the 8 queens problem, it's pretty easy to know what an individual state that's fit enough means. The goal is to find a state where none of the queens are attacking each other, right? Now there could be multiple states that fit that definition. There could be multiple configurations of the 8 queens that don't attack each other. Okay, it just says until some individuals fit enough, right? So, at the end of, as you generate each population for 8 queens, you could just have a check and you could go through as you're going through and pairing off people and reproducing. You might come across and evaluate an individual who's perfect. Well, then you can just terminate the loop, right? Or maybe after you've come up with your new population, then you have a subsequent subroutine that goes to that population and goes, is anybody here perfect? Is anybody an 8 queen configuration that is good? That's our goal. Okay, we're done. Get out of here. So you'd modify the algorithm a little bit. Just says until some individuals fit enough. How would you implement that? Well, it depends. I gave you one example right there. Or enough time has elapsed. And it might be the case where you just say, well, I only want to go through 200 generations, right? And we'll call it a day at that point. And then after 200 generations, we'll examine the population and we'll find the individual that has the best fitness function score, return him. That's the best we can do. Okay. Yeah, and so that you could have one that's good enough after the end of a certain amount of time, or until you can absolutely conclusively identify who the best is. Maybe before that time or a combination of the two, right? It's up to you. Okay, it's up to the problem that you're trying to solve. All right, so I'll put a cut in here, and then we'll start section 4.3 in the next video.